Hello and welcome to today's Wolfram Institute live stream. Today I'll be doing some live coding on the subject of all the incomplete open cubes by Sol uh, Lewitt. So for context, let's see. Let me share screen. Begin. Okay. Um, can everyone see my screen?
Yeah.
Okay. Ah, here we go. Okay, now I can see my screen. Or my Zoom can see my screen. And I'm broadcasting Zoom. All right, so it's a little confusing for me. All right. So this is a description of Paul DeWitt's artwork from 1972. So for context, that is what this is. So it's or 1974 rather. So he made this survey of all the ways to have a subset of edges on a cube such that it makes an open cube. Uh, for instance, here are all the ones that have three edges, and it's going up to a complete cube up top. Um, so, like here's a cube. Weird. Um, that's missing one edge, and then missing two edges. There are five configurations. Uh, these are distinct configurations up to rotation. So, and here are all the ones with three edges, unique up to rotation. Now, it should be noted that this is a mirror symmetric version of this one. So technically these are the same up to reflection, but we are only considering orientation preserving rotations for this. And I guess coplanar configurations are also excluded. That is, three edges of a square wouldn't be included in this list. So there should be 122 of these all total. I'd also like to refer to everyone to Three Blue and Brown's latest video, Exploration and Epiphany, a video by Paul Danstep, where he goes over a little bit of history and then like what it means to compute this list. All right. So zoom in here. All right, so it would be good to start out with enumerating the cube vertices, for instance. We'll set the coordinates at -1 and 1 to keep it centered at the origin. Okay, so 8 vertices. Have a look at this. All right, 8 vertices of this of the cube, and next it'd be good to get the all the edges of that. So this is all subsets of those vertices, including the diagonals and such. So to get the ones that are going along the edges of the cube, good to get the ones that have norm 1 or norm 2, excuse me. Have oh, there we go. All right, to get one of these configurations, it would it's a subset of edges.
But I just make it a little bit easier. So
What's that?
let's do mesh primitives. Let's use mesh primitives. Let's use better functions.
Okay, so
If you want, you can grab it from the Zoom chat.
yeah, yeah. Um, okay, so I'm trying to think of how that would tie into doing rotations and stuff.
Well, we can use like all the region transformation things, like rotation transforms. They work directly on all the graphics primitives, like lines.
Okay, let's give it a shot.
You can still turn them into a tube. I think you need to like replace all the lines with tubes, something like that.
Make this into a function here. Ah,
I think AAA Sol is always heads true, so you don't need this.
Good.
Yeah.
Yeah. It- Okay, so essentially, a lot of them. 4,096. I think that was mentioned in the video.
Yep. 2 to the 12.
Yep.
So if we're talking about different ways that we could have gotten to these configurations, what I was saying when this conversation was first starting, what I would have thought of doing is you have all of the edges and then just using the numbers from 0 to 4095 as a bit index into which subsets to add.
Right. So yeah, of the 12 edges, just
Yeah,
enumerate them, and
just
then
enumerate them, and you can enumerate them by just looking at the binary sequence. Which I don't know if it's better in any way. It's just, it's a very different view about how to cut the thing up.
Well, we can try it. Dugan, you can do it too, right? Why not? Let's instead of like all the subsets, make all the binary strings and use peak or something.
Yeah.
yeah, so essentially, with the edges as enumerated here, I sorted them. And I sorted each one. So it kind of goes in order of how the coordinates are sorted. And in that sense, yeah, you can binarize that. I don't know if I want to do that or
Yeah, no need. I was just pointing that out. You went by quickly into how you got only the connected ones. What did you do to throw out the disconnected ones?
so there you have to sort
I
out
hope that
by uh, how use the graph function. So um, let's look at one of the configurations and find one that's like, for instance, disconnected.
is there some region function that can do this? Like a disconnected region thing. I don't even know.
Okay, here's one. So we look at it as a list of lines, and we want to think of it as a let's replace line with undirected edge. Um, get this. Oh, I see. Um, take those things out of the line header and then okay. So these edges are connected over here, and then this edge is just by itself. Connected graph cube. False. Okay, so if I turn this into a function, should be 20, 40, 24, 34 of them are connected. Oops.
There's some formula you could have had that would have gotten you that number.
Combinatorics, graph theory, I wouldn't know where that type of number would have come from. Worth checking the number sequence database.
Is there an approach to sort of build up, like in a kind of more physical way? So starting with just um, one line, right? We just have one side we know that that's the only one of one. And then there's only one version of two. But then if we add a third, there's only three places we could add a third side. Is it a side? Is it a line? Vertex? I don't know my terminology. But I'm thinking, yeah, like when you start with two, then there's only one place you could, there are three places you could put a third.
Hmm.
And then once you have those, it's sort of like a graph rewriting type of approach. And then you could test to see at each stage if those are rotationally equivalent.
I see. So it's like you grow the tree from the root,
Yeah,
and then you kind of prune as you grow.
exactly, exactly. And then you only grow on the bases that you had already tested. Now, I guess that I don't know if that will work because you might miss opportunities. You might dismiss something earlier that maybe has potential later.
Right, right. So yeah, there could be a tree of decisions. Like you start with the first edge, and then from there you have like the edges that are connected to it, and you pick
Well,
one of
actually,
those.
Do you want to try playing down that path a little bit in practice? Because I think a first step along that path is realizing, okay, how many of the choice, there's only one line, right? There's only one with one line.
Mm-hmm.
Do we take that as a given, or do we try to convince ourselves of that from first principles? Because from this line, there's only 4 possible connected lines that you can add, right? You know, the line has 2 edges, and if you just follow the path from each of the 2 edges.
Oh, you're proposing that you could also possibly, you want to sort of dismiss the diagonal connections?
Well, the sculpture only has connected things, and it's only the edges, right? So
Yeah,
there's, you could put that, you could bake that constraint in at the beginning, because the line, that configuration only has 2 attachment points,
right.
right? And each vertex has 3 things coming out of it, and one's used up by that line.
Okay, yeah.
Yeah, so there
They
are
can
2
go
others.
in the, yeah. Yeah, I see. Yeah. Yeah, I thought of it as kind of essentially the same, but then it's like rotation would solve for the others.
Right. So we'll have to get rotations involved in this approach as well, in both approaches. So I should get the rotations up. Okay, so rotations of the cube. Basically, what I'm thinking is um, looking at rotation matrices and like 90-degree turns. So, however the cube is rotated, if you start with an initial frame along the coordinate axes, it'll end up putting that frame on the same axes. So,
Can't you just enumerate all the axes first? Is it like some kind of subsets of 0 and 1 of size 3?
so yeah. So there are only 4 possible. That doesn't seem right.
No. No, because there are 24 rotations of a position. But here's a very high level question. So far we've done 3 approaches. All 3 of the approaches are referring to coordinates rather than just referring to labels.
Yeah, the description that we have, the representation is coordinate based.
Right. And is there some way of thinking about the advantages and disadvantages of coordinate-based versus label-based?
Yeah, yeah. I mean,
Because
depends.
if it's
Depends on
label
depends on what
based,
you're going.
if it's label based, it's closer to thinking about it as a group rather than as an object, isn't it?
Right. I guess, and start thinking about the actions of the rotations on the labels.
Yes. Yes, because what a rotation is going to be is it's going to be an 8 to 8 like transformation, saying if it was here, it should go there for each of the 8 positions.
Hmm.
And the reason I'm asking that is if you do it with coordinates, won't we get into trouble later generalizing it to things that like are not integer dimensional or don't lay out themselves well in space?
So, um,
Hang on, what's permutations there?
oh, permutations just takes like a list and gives you all the rearrangements of it.
Okay.
So this will include things where, for instance, if you want to rotate around a diagonal in the cube, um, you're effectively permuting three of the axes as a rotation. Right. I don't know if that landed. So I'll show you. Okay, how do I apply geometric rotation to this? Uh,
Geometric transform. Did you enumerate all the transformations already? Like with angles. It's not about axis, right? It's an angle plus an axis.
right, right. So putting it this way is taking the XYZ axes and then effectively spinning them, permuting them in place. So permuting red to green to blue cyclically acts as a rotation which permutes the cube. So that's why I use permutations here when enumerating these frames. Okay, so now the question is, what happens if I do this? Okay, so it doesn't actually compute the coordinate rotation yet, right?
Make normal of it. Well, you need an actual transform. It doesn't look like it needs a rotation transform, not just a matrix. Wrap it with a rotation transform, something. Or if you give it a matrix, I think it's just a fine transform. Actually. Try a fine transform, because you already have a matrix, not some argument, so I can go. What's it doing? It does work on lines. Maybe cube is too weird because it's if you just have raw lines or points, it will transform them.
So it's saying, oh, I mean, graphics knows how to handle it, but was it mesh primitives?
Yeah.
We're getting comments on the YouTube stream.
What are the comments?
There's a lot of them. So the way I would do this is by
We're getting
represent.
comments on the YouTube stream.
One of them is, the way I would do it is by representing every configuration using 12-bit variables. That's kind of the thing that I said as well. Techniques. Can you look at it? Look at them, Dugan? There's a lot of them.
Yeah.
Memes is asking what's going on.
Oh, yeah, that's his intro.
And Perpetual Science, do we know who that is?
And then before, I don't know who they are.
I think it's Michael.
Oh, yeah, Michael Ostrom.
John Bohr was just texting me and he said that he looked at the video yesterday. So
Hmm.
very cool that we're doing this. And I don't know if we mentioned during the early part of this is that it happens to be Sol Lewitt's birthday today. So it's a really nice thing to be working on this project today. I'm also going to put another pitch in for my tree approach because I like this idea. I know that Dugan didn't think about it before, so probably needs more time to think about it. But it gives a chance to think about the rotations in a more general way, I think. Or well, I mean, this is also general.
Well, actually, would it be consistent with what you're doing to not do the full tree approach, but just do the sub-problem with only 2 lines? Or 3 lines?
Yeah, so I need to finish this rotation stuff first. The line is a list of vertices. Like M key, I think it's stuck. Rotate that. Oh. To get it back into a canonical form, I'd want to sort these things by the coordinates of their edges. That is to say, yeah. So that way, after it's rotated, it can be stored in a way that's identical to how it's listed. So that right.
So canonicalize is just doing a sort.
Yeah. Sorting each line, I think.
But if that works, can't you just do the generate the 4096 list and canonicalize them all and delete duplicates?
Oh, hold on. How applies the configurations? I don't think they are.
No, but just sorting it can't work. It wouldn't work if there was one edge, would it?
You're saying like
That to canonicalize something, you have to rotate things. Right? It's not just enough to change the
yeah,
order.
when we're deduplicating the list based on rotational equivalent. So like this one is equivalent to that one to rotation. Well, we just rotated it, but invariably somewhere there's that configuration enumerated. Here we go. So, for instance, 1324, when rotated with this rotation, will give you, configuration 2656. Let's check that. What happened? Oh. Oh, I see. I was indexing different lists. Let me make sure that. And now I have to go back to oh. Okay. So let's see. $2,000 of these. 12 of size 1, so 12 single edges, 24 with 2 edges, and 660 with 7 edges, etc. Very nice bell curve here. We want to mod out by 24 rotation. So, essentially, the way I did this, a good way to do this is to sort of take a configuration and rotate it in all possible ways. So rotate. These are the rotations of this particular one. And if I took this and I sorted it, hopefully this will be a canonical order for this thing. So how do I canonicalize a list of these things? That's a question. Oh. Configuration, rotate. The issue I'm having right now is that I want this list not to get permuted if I take a shape. So I get a list of 24 rotations of that shape, and I want that list to be uniform. Have a canonical ordering for these. Seems not to.
Do you need a canonical ordering or just a canonical one of them? Right, if you take all of the rotation, you want to pull out the one that sorts to the first.
Um, so these are equivalent. And just make sure that That's so. I'm not sure if I'm canonicalizing these things correctly. Because that would
But isn't to canonicalize something, can't you just find its 24 rotations and then take the first in the sorted list?
yes, actually. Um, that's a really good point.
Right, you've got all of the pieces to do that, right?
Again, that relies on um, us having everything canonicalized correctly. All right, something like this. So -1, -1, -1. So these are edges. These are graphical representations of each edge. And it's like it's correctly ordered. question is, are these even yeah, why are these different, you know?
There's a subtlety that may blow up this whole strategy. Depending on how the rotations happen, a particular edge may be from the first point to the second point, or from the second point to the first point. So in
Oh.
order to cannot, you've got to sort the points within the edges.
Right. And and uh, so yeah, each line has to have its vertices sorted, and then you sort the lines. Right, and then I guess this is having. I don't understand that. Yeah, it should at some point, like, unless I already sorted that out when I said rotate lines. Um, no, there's no sorting here. this one. Ah. Somehow. Sorting the line doesn't sort what's inside the line. So the
Yeah, can't you just strip off the line heads and then do all of the work and then put them back at the end?
I have to change this. So what level spec is that? I said one negative one. All right, so that oh. That might help. Mirror image of each other? Does it contain a mirror? No way. Rotate that up there.
Are we allowed to have mirror images in the
No.
set that we're looking for? Oh, okay, okay, so mirror images.
I don't know how they got in there though. Because that was a mirror image. Right? I think it was.
I think it was.
It's reflecting the x-axis and keeping the y-axis and z-axis fixed. Has a determinant -1. Uh, oh, when I added permutations, see, there it is. Okay, so when you permute two axes, it flips the determinant. Are there too many mutations here? Okay. So half these are crony. All right, so we have to do this selection again after. Rotations. Okay, so these should be rotations of each other. But it's not. No, it is. Around the diagonal axis. If you sort of true. There we go. Okay. Perfect. Oh no. How do I subtract a set? Complement. Try it and hope for the best. All right, so I have a configuration. I'm going to canonical form for it. I can take the rotation list, sort it, take the first stat. Hopefully. Um, How many were there supposed to be? 112 or 122?
You didn't
and
remove
22.
yeah, you didn't remove the flat ones, did you?
I didn't.
How many families again? 122?
Yeah,
I'm getting 123. Hold on. Almost there.
Nick, did you uninclude the null one?
I think so. Oh, no,
there,
I didn't include the full one. Yeah,
Yeah.
right. The full one is also not there. It's incomplete. Yeah.
there are a lot of people who want to share code, I think.
Yeah, it's almost like when we were doing this, we should have had an open Zoom meeting since like lots of people wanna throw in their ideas.
I wasted a lot
Yeah,
of time trying to get the rotations from some entity data and lattices things, cubic lattice symmetries.
You know, it's almost worth a separate discussion once we have the answer is what would have been the efficient path through this.
the tree approach.
Well, you know,
I'm convinced. I'm convinced that it has. There's like a lot of really interesting recursive lessons, but it's a completely different way of approaching it, right? It's like building it up from pieces rather than starting with the idea that we can generate all possible solutions and then just test them and filter them out. I'm like making all these little drawings. Instead of coding, I'm like doing a lot of drawings in different canonical forms. Very fun.
So when you say the tree approach, so you start with three, I guess.
You just start with one.
Okay, because the original constraint didn't allow for one or two.
Yeah, well, okay, you can start with then two. And then you put where there are three different ways to make three from two, right? Or actually, there's more than three ways. I think there's six ways to make three from two. Right. One, two, three.
No, because one of the things, and it's again that this may be a different discussion to have a different day, is the various approaches. Because somewhere like not quite at the tree approach is if we would have done this not for the whole set, but for the set with n edges, it may have been more debuggable because then we could have tried three and three, and because that wouldn't have been too bad, and then we could have tried four, and it would have been a little bit bigger. So by the time we got to six, we would have been confident that we had good code.
Okay, we're
So
not.
Nick, did you
Yeah, here's some flat ones. So we need to get rid of the flat ones and the road. There. Okay, so if we
By the
have
way, I
a,
did it when I had like a simple select at the beginning. When I was selecting for connected ones, I also selected for whether the convex hull is three-dimensional, something like that.
It's convex hull.
see how do I convex hull mesh will give you given a set of points, wrap a mesh around it.
Okay, and then how do you find out that that's basically flat?
I used region dimension because it's when you have a region, it can determine whether its overall dimensionality.
So the convex hull, the region dimension, and we want that equal to.
That's cool.
Yeah.
That's a good trick. How does the convex hull or whatever work with disconnected when the graph is like disconnected like this, Nick? Would it shape over the whole both objects, or would it do two separate things?
I'm gonna do over the whole, yes. So we need to disconnect connected first, or
Right.
whatever. Just
So that's not a way to deal with the disconnected ones.
oh, there's a function that determines disconnected components for the mesh too. I was doing this
Yeah.
like with meshes like
No,
this.
yeah, no, I was
String.
just thinking it could do both at the same time.
Yeah, if you like had a list of edges as a list of graphic primitives, you can turn them into a mesh, and then there's a function to make a convex hull of it, to determine the dimensionality, or just select all the disconnected components and count them. And so basically that's the filter. There's one connected component and the dimension is free.
Okay.
There's another gotcha was with the rotations. Technically, of course, you have to count the identity. Yeah. So there are 25 transformations. So if you forget about that, you're not gonna get the right thing. And also like trying to extract all the rotations from the group that I was trying wasn't working directly. I was kind of trying to compose a bunch of them so that and then take the union. So the row transformation that the group or maybe I'm doing something right. It wasn't like a full list of rotations that were correct or something like that.
I need to apply a union before. So we're starting out with the ones that are at least 3 edges.
Can't you do it in more of an arithmetic way that for each of the 3 axes, see if any of them have all of the same values? Right, it's like the or of the not all equal.
Can you say that again?
On a dimension by dimension basis, for it to be flat, at least one of them would have all three, all of the points having the same value.
When you just look at the vertex set,
Well, they could all share an x value of -1 or an x value of +1 or a y, each any of x, y, or z could be all -1 or all +1.
wait a minute.
No, it's very interesting. There's been a lot of subproblems here where there was a choice between doing something up from the bottom or doing something using a clever function.
I'm getting I see. I see. So like giving me an error. Complex Hull is giving me an error. What's that error? This needs to be 4 or more independent points, and it's not. It doesn't like. Like this for some reason. It doesn't take the convex hull of something which has dimension 2.
But Nick, didn't you say
Need to
you were
flatten
using
it.
it for this sorting?
So what?
The Dugan just said it's convex hull's not working for a flat thing.
I was running on the list of lines. Maybe I don't know. Maybe it's convex hull, not mesh, but convex. Where is it? I was using convex hull region.
Oh, Oh, of the lines. You can apply it to.
I think you just give it a list of points, flatten it till you have like some very nested thing.
Um, oh. I'm unfamiliar with this function. All right, so there's no error so far. Well, I got it down to 326.
I did post my notebook if you want to check. Compare.
Thank you for rounding them. Oh, is that the right answer?
Yeah, well, they said 122. I haven't checked myself. I think so.
I think we're allowed to keep mirrored ones, right?
Yeah, if you look at, I think it was the second bottom line, there are two that are mirror images of each other.
Yeah, I think he just didn't want flats and rotations. I guess presumably flats aren't cube-like enough.
Why do you have 25 rotations?
It's transformations, technically. So it includes identity.
Shouldn't it still be 24?
Well, turns out not. I don't know. I think it didn't work without it properly.
Why not have? Must have some sort of duplicate.
There are 24 rotations, not 12. So if you only had 12, then it's not going to be filtering out enough.
And it's not going to have the same thing. Right. It might. So where did I go wrong with my rotation? I guess. The way I made my rotation group is incomplete. So if I just do this.
It's an interesting question of whether or not it's cheating to be looking up crystallographic data.
I like cheats like that. It's like usually learn something new from them.
What's the name of the group?
Well, I think there are actually multiple that were working right. I was like trying to search for entity stores. Like for the lattice, there's a simple cubic lattice, and it had multiple groups with the same order, like order 24. And I think like if you do it, basically there are multiple groups. I don't know what this name actually means. Like th, there's some all group, basically this with the same result.
Is there tetrahedral crystallographic group?
Yes.
I think so. Yeah, I've seen like tetrahedral
Yeah, I mean
there
every,
somewhere.
you know, you're looking at the rotation group of that operates on the tetrahedron in that case. It might not be a crystallographic group because tetrahedrons don't crystallize space, they don't form a regular tiling. Okay, so this is the identity. We can get rid of this. Okay, so. Okay. So how did I apply a rotation? How do I apply a rotation to a configuration?
It's a just geometric transform, normal of that.
You just get the
So Nick, what did you do for canonicalization?
No, I think basically the same what Dugan was trying, like sorting, taking the first, sorting the lines, the edges, coordinates.
But did you have to sort the point ordering within the lines?
I think so, yeah. Well, that's what I've done at the beginning, like when I just extracted the edges. Okay, that's what my canonical ones. Okay, I sorted it right there at the beginning, and then I just looked them up. I was operating with the indices of those edges instead of the edges themselves.
okay. All right, this might help. Good. That actually looks good too. All right. Whew.
There it is. Right, you probably also have to remove the full one.
Yep.
So if we wanted to sum up what we just went through, the overall strategy was kind of good. There was just the sub problem of picking all of the rotations that didn't work until you did what I call cheating, but Nick says is just cleverness. So actually, Nick, since you had interesting ways of solving various subproblems, could you think of a different way to deal with duplicates up to rotation?
Not really.
So that
Just
there is,
just typical brute force if you have all the transformations. I don't know.
does that means that with all of the graph functions, there isn't something in graph function land that would provide some help?
Maybe if you will want to deal with the actual group and maybe some kind of Cayley graphs, perhaps.
Okay, but there isn't just, are these two the same?
I don't know. I'm not sure. It's like I already figure out how to at least pick the right rotations out of the group somehow. I think you can simplify it even further.
So are the crystallographic groups actually crystallographic, or is that just a name for groups?
No, well, I think they come from crystallography. So they,
Okay, so they come
Well-
from crystallography rather than coming from math.
yeah, I think so. They basically all around symmetries of these lattices in crystals.
Can I do a geometric translation? Doing something wrong, Nick? Oh, no, it's working. Okay. The approach worked. My goodness.
Success.
Make this tubes.
Just looking at what is discretized graphics?
No, that takes the graphics as a object, graphical primitives with all the lines, cubes, and turns them into mesh regions. Those are like a different data structure.
So it's kind of like rasterized, but going into something that isn't bits, but some other data structure.
Yeah, more useful for actual just geometry, right? Graphics may contain a bunch of directives like colors and all that. I think it strips away all that, even though meshes even can be colored. But extract all the necessary information to make a region. If there's some lines, cubes, spheres and all that, and turn them into regions that can be unioned, do some discretization of those, compute volumes, do actual geometry on top of them, not just display them.
Okay, and the lowest level of doing geometry is regions?
I think so, yeah.
Okay.
Even the primitives, some of the graphical primitives are also regions. Like line is kind of both a graphical primitive and a region. But yeah, there are different kind of regions. Mesh regions, simplicial complexes, things like that, that you can just combine a bunch of primitives together.
So this is all good. Do we need to do a second round because we didn't move
Well,
on
it'd
to
be fun to
tetrahedron?
like adapt this to other polytopes, you know, like the platonic solids, let's say. Or
Well,
what was said
if
for
we're
the
talking,
tetrahedron, there were like 12 of those.
yeah, and that should be a lot easier. The thing that I found interesting about this is it did seem like a central part of this was figuring out how to get a list of rotations. And it did seem like, yeah, Dugan, what you did was like fundamentally different than what Nick did, which was also completely different than what I thought it would have done. But there were some good ideas there. The thing that I thought was fairly interesting, Dugan, is you well, we started off with kind of like mesh primitives
Mm-hmm.
and rotates.
Yeah.
It may have been interesting to go from mesh primitives and rotates to some kind of permutations or some kind of list reordering.
Right, right. To sort of
Right. Right. Because it did seem, and this is what I was saying at the very, very beginning of this, it does seem like if you wanted to be playing with groups like this in the most general form, being attached to geometry seems like a limit. Right. You know, that what rotations are is they're just generalized reordering of vertex lists or of edge lists. And it could be that using the techniques that either of you two used to actually get what that list is good, but then having turned that list, you know, because Nick, you did turn you were at the end of the day using labels for the edges, right, rather than the actual lines.
Kinda, yeah.
And you know, just having a rotation be reorder that, you know, the list of edges, you know, with this goes there, that goes there.
Maybe, yeah. Maybe like the permutation group of that crystallographic group exactly doing that, but I'm not sure.
It's possible that it did that, but it would mean that what you could feed into it doesn't necessarily have to have a crystallographic group. You know, does seem to me that, you know, when you're working on a problem like this, or at least when I'm working on a problem like that, the critical thing is to try and figure out what the right representation is. And the two things that we seem to be figuring out what we wanted to represent. One was configurations, and the other was rotations. And Nick, I think you settled on having configurations being basically a list of labels, right? Or list of indexes, more precisely.
It's kind of both. It's like I'm maintaining it as a list of indexed edges, but
Yes.
then I look up the actual edges as lines in order to rotate them, then look up the indices for those rotated
Right.
lines,
And
and then
what I was
canonical them.
right, what I was suggesting is you could have done an extra layer of crunching of the crystallographic transformations to make it unnecessary to,
Yeah, I
you know,
think so. Yeah.
to go back to the lines level until the very end when you wanted to plot it.
Yeah. Yeah, I'm pretty sure we could. All the transformations can be extracted from the group by just like having some permutation equivalent
Right.
of that.
And
Yeah.
it just intuitively feels to me that that representation is closer to what's going on in the problem.
Yep.
But no, this was a really instructive exercise for me, at least.
Well, we are glad.
I have all sorts of crazy ideas about like alternative canonical forms for the cube and stuff.
Would it make sense to schedule a second round of this rather than, because we've already been at it for 2.5 hours?
Yeah, I gotta get going. Let's try to do something here. Trying to canonicalize like what edges from the edge list to do what you say, Brian, of saying like this configuration is this selection of edges 3 and 4, I guess.
Yeah, it's essentially, I think that if I wanted to extract what I was saying from it, the representation of configuration should just be a list of length, number of edges. And what a rotation should be is I'm not even quite sure what the right word to use is. It's like the swapping rules for what to move around to get to a different configuration. And
Permutation.
yeah, it's a permutation, but the way permutation was being used as the name of a function, it's not quite right. It's not quite that, right?
No, it's I think it's more general than that. It's take some list of indices for edges and permute it with some kind of element of the group. that,
Yes.
that-
Yeah, but that's precisely it. Is, what it's doing is figuring out what's the cleanest way of representing, because if it's a member of the group, basically what we're calling rotation is just the main operation of the group, isn't it?
yeah, exactly.
So it's again, the whole core of the suggestion is, just have the representations be closer to like group think, haha, than geometry think.
I agree.
So, for instance, um,
Because again, Dugan, once you've done that, if you want to do the other Platonic solids, it's just recreating that one thing. Again, what I was saying at the very beginning of this, the thing that I haven't really developed an intuition about, but it's getting better, is the way that those rotations come out of symmetries, and there must be a way of creating that permutation list just by having some language to describe the symmetries.
I think that's what Dugan is trying to do, right? Just if you have this very brute force naive way of constructing rotations, we can just rotate all our edges, but then see how that actually transforms the indices, and then we can recover the permutation group.
No, for sure, for sure. But in order to, once you have that list of rotations, once you have the list of permutations, you're good to go. So the questions is, what do you feed in to get that list of permutations? At some level, you'd think that you only need to say what the symmetries are.
Yeah.
yeah. I think that, for round 2, do that some other time. That'd be really cool.
Okay, well, I guess happy birthday, Sol.
Yeah. Happy birthday to Sol Lewitt. Sol
Sol
Lewitt.
Lewitt.